we're going to kind of do what we did before, where you guys, every time it seems like you're my first review session, so it's always the bumpiest. And actually, I'm not done kind of scrolling out my reviews notes. But this one, I got chapter 5 in pretty good. So different types of cousins, right? So you probably want to put this on your note card. The short wavelength to the long wavelength. Can you kind of see them all in there? And I am going to make this available, so I don't know if you'll have time to write them all down or not. But the next one says frequency and wavelength, and I put in green kind of like frequency with regard to gamma rays. That's the highest frequency. And actually, it's also the shortest wavelength. So gamma rays, highest frequency, shortest wavelength. You can kind of picture that figure from the textbook. And then when you get clear down to radio waves, that last cousin, it's got the lowest frequency and the longest wavelength. Hi, come on in. No, you're fine.
It was raining, so
I know.
when I left North Campus, couldn't see me.
And it's got the longest.
That's
You go from
wavelength.
Burlington
Wavelength.
to here.
She's
Her
got long
classes are-
Thursdays.
I got classes in there.
But you live in Hamilton, right?
Right.
And then, and I was telling them that this, if you can, like this whole slide, it's going to be a PDF that you can get off of download. So,
Okay.
Even with your writing on it?
yes, that's the point. Yeah, with my writing on it. It won't have the builds, but the video is being captured, so you have to listen to the video, but that's a possibility. So we're on the third one, structure of an atom. I made it up there in the kind of the corner. So the only things we worry about are three particles: protons, neutrons, and electrons. I think you had a homework question where you, so kind of be able to do that. Structure of an atom, it's all good. And so the nucleus has the green protons and the kind of the purplish neutrons. The electrons are outside the nucleus, the structure of an atom. So the next one, kind of related to an atom, we have atomic number and atomic mass number. Okay, so atomic number there to the left is the number of protons, little smiley face. And actually, with regard to atomic number, I have in green, the atomic number of protons defines what element the atom is. And then in blue, atomic mass number, I have up there kind of already with blue with regard to the subatomic particles. Atomic mass number is looking in the nucleus at protons and neutrons. Atomic mass number. And then the whole light interacting with matter, we just kind of said there was a slide that said light can interact with matter one of three ways. That light can be transmitted, that light can be absorbed, and that light can be reflected or scattered, kind of similar. I just think it's neat because which of these three happens depends on which energy it is and what the matter is. That's so cool.
What is the last one say? Sorry.
Reflected / scattered.
Okay.
And then the three types of spectra, I actually went out on the internet and brought in something new there. You can kind of see the colors in kind of purple and green and red next to the three types of spectra. So this one, this top one, it says continuum. We call it continuous, but continuous spectrum, same thing. No lines. And then I also said that you can determine the temperature. You can determine temperature with this one. And then these have to do with electrons. Okay? Note these lines are fingerprints of electrons. And this one right here, this emission line spectra, I have in green. Excited electrons fall back down, emit energy. That's that middle one. That's Kirchhoff's second law. But I don't think on this test I ask which of Kirchhoff's three laws. You don't have to do that this time. Okay, and then this one down here has to do with electrons too. Electrons become excited, and this says, and use energy. So kind of these two right here, that says 3 types of spectra and electrons transition between energy levels, those are both addressed kind of here. Okay. Electrons, are they going up or are they going down? Well, for emission lines, they're coming down, and for absorption lines, they're going up. Emission lines, they're releasing energy, and absorption lines, they're sucking in energy. And then 2 types of telescopes. 2 types of telescopes I have in green and red up here. 2 types of telescopes. Reflecting telescopes use mirrors, and then in red I say refracting. There's too many R's. Refracting telescopes use lenses in red. And the next term is related to focal point of a telescope. I kind of do the 2 types of telescopes here. This one is a mirror where you have light coming in and it bounces off the mirror. That green part is the focal point. Okay, so this is a reflecting telescope. And this, just a terrible drawing, but this is a refracting telescope that uses lenses to bring the light back to a focal point. So there's the 2 mirrors. And then angular resolution, I just simply kind of squeezed in here in red. Angular resolution is talking about the ability to resolve detail, able to resolve detail, angular resolution. And then the red and blue shift, it's specifically when you look at these spectral lines, if something's moving towards you or away from you, I kind of wrote down here. Okay. I know this is kind of in the way. I need to make that not show up.
Is the source moving away
From, this should be observer. Source moving away from observer. Spectral lines at longer wavelength.
Are red, right?
That's redshift. Mm-hmm.
I remember that.
And then the blue, okay, is the source is moving towards observer. Spectral lines at shorter wavelengths. And then the last thing I have is telescopes in orbit. And I kind of put it clear up there in purple. So why do we put telescopes in orbit? And there's kind of 3 reasons. One is because of Earth's light pollution. And then the other 2 have to do with the Earth's atmosphere. The second one is there's turbulence in the Earth's atmosphere. And the third one, that circle with a plus in it, is Earth. And it's supposed to say Earth's atmosphere absorbs energy. So yes, I will definitely make that available.
Okay, what was the third one? Sorry.
Oh, that's okay. Earth's atmosphere absorbs energy. Yeah. Okay. So then chapter 6, okay, terms. First one is just solar nebula, and I say what our solar system formed from. And the next one's kind of related. Okay, the 4 ingredients, and they're in green and then red up here, the 4 ingredients in the solar nebula. Remember, hydrogen, helium was by far the most abundant in what ultimately became our solar system. And then we have number 2 there is H, or hydrogen containing compounds. And then in black I put what those compounds are. Of course, water's a compound, CH4 is methane, NH3 is ammonia. So those were by far the most abundant in our the solar nebula that became the sun and the planets. And then I put them in red because they were kind of different with regard to the temperature at which they could go ahead and come out of being a gas. Then in much minor amounts we had rocks and metals. And then I'm almost running out of builds I have. So here, with regard to collapsing solar nebula, I put in orange here, because we talked earlier, if something collapses like this and it's spinning, just like a skater, it's going to spin faster. So that's what our solar nebula did. And then the other thing, or another thing we talked about in, I think it was chapter 4, was when something goes from being large to being small, it's converting potential, gravitational potential energy to thermal energy. So it becomes warmer. So it goes faster and got warmer. Okay. Then we get to trying to decide how to do this. Okay, I don't have the others made, so here we go. The moons forming around the Jovian planets. So do you remember in your book where we saw the sun was starting, it hadn't turned on yet, and we kind of had dust in our solar system, plane of the ecliptic. And then they showed Jupiter over here, and Jupiter had its own little accretion disk, okay? So, let's see, I guess I would say something like, pick Jupiter, okay? This is going to be Jupiter, and Jupiter has its kind of own swirly material around it that ultimately, and we're going to talk tonight, where this stuff formed Jupiter's moons. Let's change my color here. So that's not the sun there, that's Jupiter. And I guess to kind of emphasize, I guess these should be kind of on different tracks to form different moons. I'll use the word accretion because I think it's a term coming up. Basically, the moons of Jupiter accreted. Accretion disk around the Jovian planets. Okay. Anomalies of our solar system to be explained. One of them I know would be, for instance, Earth's large moon. Earth's large moon. Another favorite is Uranus's tilt, crazy tilt. Crazy tilt. Okay. I think this was one. I'll go ahead and list it. The fact that, remember Pluto got demoted because there's all these crumbly stuff out there? You know, like we call that the beginning of the Oort cloud, kind of comets and stuff, like leftovers out there. I'll go ahead and just say the Oort cloud / leftovers. Leftovers. And in general, we're talking about comets and asteroids. Stuff that isn't a planet. I think that'll probably do. Oh, those are anomalies. I don't know if this is really an anomaly. 2 types of planets. I bet you guys could tell me they're the terrestrial and the gaseous, right? So terrestrial are rocky. And then there are the gaseous planets. Differences. Which one do you think is smaller? Right, very good. Rocky, terrestrial are smaller. Very good. And gaseous are larger. Any other differences?
Well, you can't.
What they're made of, and you can't stand on one, but you can stand on the other. I like that. Very good. So we'll just say composition. Composition. And surface. How's that? I'm liking all of those. Accretion in general is kind of where a planet gets larger and larger, or an object that is going to become a planet. It's planetismals first, right? So I'll go ahead and use that term, planetismals. Get larger over time because matter's kind of coming together. That's accretion. The frost line, it separated the terrestrial planets from the gaseous planets, right? But another thing, or the reason it separates it, is based upon the temperatures at which stuff will condense. So frost line separates terrestrial, Jovian, and it has to do with, I guess we could say, how about this? Rock condenses at a higher temperature. Yeah, I'm liking that. The Kuiper belt and the Oort cloud I mentioned just a minute ago, but the way I think of them is, if this is the sun, I'll go ahead and kind of make it like a star, and then we've talked how this is kind of the plane of the ecliptic, okay, and we'll say the last planet out here is Neptune. Then the Kuiper belt then basically extends out beyond that. So kind of where I have that's Kuiper belt, okay, out beyond the orbit of Neptune. Okay, so that's the Kuiper belt. The Oort cloud is a little more three-dimensional. So the Oort cloud is farther away from the sun, and it's spherical. So I don't know how to make it on here. The Oort cloud, I'm just going to put farther and spherical. With the sun in the center. Not bad. Okay.
That's a long chapter, by the way.
7?
Yes.
Oh.
It was long.
It looks long. Look at all those terms up there. You're like, really?
It was interesting.
Good. Earth's tectonics is basically, I'll just call it crust for now, but chunks of crust floating around on mantle. That's plate tectonics, kind of how I think of it. Chunks of crust floating on mantle. We'll have to kind of talk about what crust is. You kind of have an idea, and kind of underneath the crust what the liquid mantle is. Oh, on the next slide. So I'll probably, eventually when you see this available to you, I'm going to bring in probably a little figure to kind of show. But here we have, I'll start with the inner core and go that way, kind of building from inside out. So basically, all of the terrestrial planets, which is this chapter, have this kind of configuration. So we have the core, okay, and I'm not going to emphasize it much this semester, but honestly there's an inner core and there's also an outer core. Okay, you can just kind of combine those together for now, I think, if you want. But after the core, we have the mantle. And then beyond the mantle, we have the crust. But the one thing I didn't say yet is the lithosphere. So here's the crust, and I'll go ahead and make kind of breaks in the crust. Those are kind of like they can move around a little bit. Okay, so that's the Earth's crust. It's crunchy. So the lithosphere basically is the crust and the first part of the mantle. Let's see if I can kind of zoom in here and snag it. So the lithosphere, you have to take the whole crust, nothing but the crust. Now you take the whole crust and you go down a little bit to the solid part of the mantle, and that is the lithosphere. So when we talk in plate tectonics about stuff moving around, it's actually the lithosphere moving around, which takes with it the top part of the mantle. Convection is where, actually convection is what's driving our plate tectonics, but the deal here is, if we were to look at the Earth's core, okay, and this is the Earth's crust up here, basically we have a fluid part to the mantle, and this is hot, the Earth's core is hot, and so actually what it can do is heat up the liquid part of the mantle right next to it. So it makes this blobby liquid mantle hot, and just kind of like a lava lamp where fluid gets hot, it will rise. It cools off at some point as it gets farther from the core that's hot, and it will cool off and it will sink back down. Then it will heat up and it will rise. So actually, kind of that little circle I've drawn up here, that is convection, okay, where you kind of have rising, cooling, and falling back down. Heat getting hot, rising, cooling, falling back down, getting hot. It's kind of like a lava lamp. And that is actually kind of at the crux of what makes our plate tectonics move. Planetary differentiation, I love that term. And I'll tell you in lecture tonight, it's kind of like if you have ever had Italian salad dressing, and you know you have an oil component and a water component to your salad dressing. If you let it set, the more dense water is going to fall and the oil is going to float. Okay, so that's kind of what happened over time with stuff on our terrestrial planets. Basically, the heavier stuff sank to the core and the lighter stuff floated. Okay, so planetary differentiation is that heavier stuff sinks, and with regard to planets, kind of forming layers. Okay, so planetary differentiation, heavy / dense material sinks. In this case, with planetary differentiation, we're talking about the stuff that's come together to make that planet. The heavy stuff sinks. Surface erosion. I've got some slides coming up tonight, and basically there are things that you might, one you may or may not think of, and that is plate tectonics themselves. Plate, or I don't have to use the word, but tectonics. Tectonics. Ooh, no H. Tectonics. Final answer. Okay. That's one thing that kind of has resurfaced the Earth's surface. Another is wind. Okay. Wind kind of smoothing it off. Of course, we have water erosion. I think the example is the Grand Canyon. That little river has carved out its own little lane. So water, I think that should do. The next one is one of the memorable features on Mercury is that it's got these cliffs that actually we call scarps. S-C-A-R-P-S, scarps. And it's thought that these cliffs were formed basically as Mercury cooled. So that's the answer, when Mercury was cooling. Okay, I think it's a multiple choice question. How are they formed during cooling? Okay. The Caloris Basin, and I think on your test this is one of what planet is it on, I think, and it is on Mercury. It's really cool because Mercury is pretty darn small anyway. It's not much bigger than Earth's moon, Mercury, poor little Mercury. And after it had already formed a kind of nice little solid crust, basically it got whacked really bad and it formed this Caloris Basin. And if you look on the other side of it, it's got these weird jumbled rocks. So basically the energy went through the planet. I mean, planet didn't like fall apart or anything.
That's kind of cool.
Mm-hmm. That is cool. And I think the next one is like, what planet's it on? And actually Valles Marineris is the big boo-boo on Mars. On Mars. And I'll, just to kind of maybe make you remember it, actually it's in the equator, or near the equator, near Mars equator. And then actually the next one I think is going to be an extra credit because it's not in my notes. Okay. But when we talk about Venus, you're going to see some topography pictures of the surface of Venus. And the thing about Venus is it's shrouded. You can't see it in clouds. It's like, dude, how did you get those? And so the answer to that is basically they had spacecraft orbit Venus and they did it via radar through the clouds. Okay, so mapping Venus's surface via radar. My radar gun. Okay. If I just put via radar, yeah. I'll go ahead and put satellites in orbiting satellites. So they orbited the planet Venus. Cool. And I can't remember greenhouse gases. I can't remember. There might be a couple questions, but today, you know, greenhouse gases are like in the news and all that. So you probably have a sense for what they are on Earth, and they're the same for other planets. We're going to see that Venus has like a crazy amount of greenhouse gases. So greenhouse gases, they trap, let's see, they trap outgoing heat. They kind of serve as a blanket, like we put a blanket on at night to keep our heat in.
And they're only on Venus?
No, they're on Earth, they're on, yeah, they're not only on Venus, but
They talk about the greenhouse effect all the time,
Oh,
happening.
yeah, that's
Mhm.
what makes Venus so hot. Yeah.
yeah, exactly. But I can't remember, I'm gonna go ahead and add the few, I think, that are listed. Of course, you guys know carbon dioxide, CO2 is a greenhouse gas. I'm going to put H2O, of course that's water, but I'm going to put a G after it so we all know we're talking about liquid water. I think methane is, that's that NH3. Go ahead and put that one. And actually there's a slide that says nitrogen gas, which the formula for nitrogen gas isn't just an N, it's an N with a 2 because it runs around 2 atoms. So nitrogen gas, that's like most of the gas in our atmosphere is nitrogen.
So if you just said nitrogen and didn't put that in too, would it still be the correct answer?
For this class, it would be, yes. For my chemistry class, no. So the thing about Mars is that we really can tell that, I'll go ahead and, this where it says flowing water, I think all I need to say is, now I can't remember what the question was. Flowing water. I'm going to put Mars once had it. How's that? Mars once, and it goes along with the question above it, or the tickler above it, once had this. How's that? Flowing water. Of course, Earth still has flowing water. Okay? So what I'm hoping with that reminder, do you guys buy this, that Mercury never had flowing water, okay? And Venus, I don't think there's any proof that it did either. Venus is geologically active in it. But anyway, so back to the other question. How did it lose its, Mars lose its atmosphere? It's kind of a stepwise process, so I'm going to put step 1 in Mars losing its atmosphere. It cooled quickly because it's little. Step number 2, in Mars losing its atmosphere, it lost, and actually it's a term, the last term here, I'm going to have to explain what this is, but Mars lost its magnetosphere. That's step number 2. Okay, it cooled down quickly, and because it cooled, it lost its magnetosphere. And step number 3, the solar wind blew away its atmosphere. Solar wind blew it away. How's that? Blew it away. Step 1, 2, 3. So let's go in order, though. The Phobos and Deimos, because I want to get to the magnetosphere, but Phobos and Deimos are moons around Mars. This test this semester, it seems like I give you some names of moons like that, and I want you to tell me which planet they orbit. So Phobos and Deimos, I'm going to put look like potatoes, because they do look like potatoes only a mother planet could love. Okay,
They're
and
fairly small, aren't they?
they are. And they orbit Mars. The red color of Mars, I'll kind of jot this down here. It's red because of, I'll just put rust, and then I'll explain what I mean. Okay, rust, basically the iron oxidized. And have you ever heard of like iron oxidizing? That's rust. Yeah. Like the element iron. Okay, so magnetosphere, what is it? Tonight we'll kind of show you a good picture, but basically it's a protective orb that goes kind of beyond a planet, and planets that have liquid in their core can have this protective orb. Okay, so it's protective, and I'm going to say planets must be liquid. Planets must have liquid core. Or some liquid in there. And so, which planets have this?
Terrestrial planets?
Yeah, and the Jovian planets have a crazy one too. So, but you're right. Which Jovian planets have it? Because this is that chapter on Jovian planets. I would say Earth.
Chapter 7 is? I think so this is the chapter on
Yeah, 8.
terrestrial.
Yeah, 8 is the gaseous planets. So Earth has a magnetosphere, and Venus rotates too slowly, and Mars is cold. So Earth, I'm going to put is equal to big, has a big strong one, and then I'm going to say Mars still has one, but it's pretty puny. How's that? Mars, with regard to magnetosphere, is wimpy. Okay. Last chapter. Oh, this is nice. See,
What
look at all
about
this.
magnetic field?
What's that?
What about magnetic field?
They are the same thing. The magnetosphere and magnetic field are synonyms.
Oh, okay.
Good question. Okay, so these mean the same thing. Two terms are same. They remind me of like a comic book sort of character. Magnetosphere. Okay. So doesn't this look like less of a list? Isn't that nice? And actually the first one is all, the first line up there, all Jovians have rings and moons. That's all I want you to know. I want you to know that Jupiter, Saturn, Uranus, and Neptune, although we think of rings around Saturn, rings around all of those. And sometimes we might think about moons around Jupiter. All of them have moons. Okay?
You mean less than 3?
Less than 3?
I mean, what's that? 3?
Oh, that's a heart.
Oh, I thought you meant less than.
Yeah.
Oh.
It's like less than 3. Yes, that's my heart.
No, they actually, some of them have.
Like 60,
Yeah.
yeah. Yeah, somebody's like, there's like, I can never remember how many they have. They're like, but I'm like 60s for the two closer. The Jupiter's the biggest one, and then Saturn. They have a lot. But Uranus and Neptune have moons too. Let's see, compare Jupiter and Saturn's densities. And so tonight we're going to talk a little bit about this. And basically, oh, I know, this is a fun way to think of it. Saturn can float on water. So I'll just put it this way. Saturn's density is less than Jupiter. Okay, so Saturn's density is less than Jupiter. And then, I don't know, kind of still related to you answering the question on the test, the thing about Jupiter is that, how do I say it? It's so big it kind of compacted itself down. So I your textbook has a picture of like pillows. Who is that?
Yes.
Yeah.
Sorry.
Jupiter has lots of mass, lots of matter, lots of material, lots of gas. Material, it's mostly gas, that is compacting it down.
It's
Lots
the
of-
biggest planet too, right?
Right. Yep. That makes it not so fluffy. What drives Io's volcanic activity? So, first off, I want you to know, probably for the maybe for the test, maybe not, that Io is one of Jupiter's moons. So Io orbits Jupiter. And it's the closest one actually to Jupiter. And its volcanic activity comes from tidal flexing. I'll go ahead and write it down, then explain it. Tidal flexing. Let's see. And next to it, I know, I'm going to put stress ball. We all should have stress balls. And if you, I don't know. I think I have one somewhere in my desk. But if you're familiar with what a stress ball is, you know, and it's similar to like a rubber band. If you take a rubber band like this, it's going to get hot. Okay, and so kind of that is flexing your material. And so Io is like this, and the reason it's like this is because the tide, it says tide, right? Tidal flexing, but it's like gravitation, tidal gravitation of other moons. I know. Here, I got it. Gravitational pull of other moons. Tidal flexing.
That makes a lot more sense.
Good. I'm going to say gravitational pull of passing moons. Like in.
Passing.
I like that. Of course, we kind of have twins. We got Jupiter and Saturn kind of have that orangish reddish look, and then we have Uranus and Neptune kind of look blue, and they are blue because of the presence of, I think it's methane. I'm almost positive. Let's ask the Google. Oh, that's right. I'm not on the
Online.
internet. Yeah. Because that's what sticks out in my mind. Is it methane? Okay. Okay. I'll check at break. If it's not, I'll let you know. But we skipped one. Saturn's rings. Basically they are reflective, means they're shiny. Reflective ice. Ice and rock. Little bits that are kind of orbiting Saturn in kind of a frisbee sort of thing. It gives it this ring looking. But all gaseous planets have rings. Triton is a moon around Neptune. I'm going to say orbits Neptune. Well, I'm going to put it down at the bottom here because I don't know. I guess it didn't make the review sheet, but I'm going to go ahead and say Titan without an R, and it's A instead of O. Titan is a moon that orbits Saturn.
It is because of the methane.
Okay.
It
Thank you.
reflects off of the methane. Something that it said something reflects off
The other colors are absorbed in,
yeah.
in methane.
The sun reflects
scatters.
the blue light.
Blue. Thank you. Thank you. Very good. The moons that Galileo saw, which I think is so romantic. Well, the one is Io. You already heard about Io. And then we have Io, Ganymede, Gynamede, and I might be butchering the spelling. Gynamede, Europa, and Callisto. Callisto.
Are they all orbit Jupiter?
What's that?
They all orbit Jupiter?
Yep, they all orbit Jupiter.
Those were the moons.
Galileans. What's that?
They're the moons at Galileans.
Yep, orbit Jupiter. Jupiter. Very good. And then the last one, it's kind of crazy, but we're going to say how three, if not at least two of the Galilean moons, and then one awesome moon for sure that orbits Saturn, have these this tectonic activity. But you know how we just now talked about tectonics on Earth, you know, kind of the plates moving, but there's a figure that's going to kind of do a good job in explaining this. But the icy moons of Jupiter and Saturn go like this. If you're looking at them edge on, so here is kind of the inside of the moon, okay, that's around Jupiter or Saturn, and it's very cold. And basically what we think is that there's liquid water, LIQ for liquid water, okay, kind of moving around here, and then it's got crusts of ice, okay, and it's not having crusts of rock, but basically I'm kind of trying to show you these slabs, okay, so this is crust. I'm going to put ice crust. So ice crust, solid, moving around on liquid water. Is that not cool or what? And I don't think I call it out by name, but one of the moons of Saturn is called Enceladus. And Enceladus, actually, they've seen like, well, it freezes, but they've seen water coming up from little fissures in its crust. Yeah. Okay? So we have a little bit of time to have a break, and I'll be posting these. And question about that?
Wish me luck. I went to two different